After studying this module, you would know the concept of the derivative and the rules of derivatives, learn about differentiability and differentiation, know about the economic applications of differentiation.
In this module, we will study the concept of derivatives and the rules for derivatives. The derivative of a function of a real variable measures the sensitivity to change of a quantity which is determined by another quantity. It is a fundamental tool of calculus. For example, the derivative of the position of a moving object with respect to time is the object's velocity. This measures how quickly the position of the object changes when the time is advanced. The derivative measures the instantaneous rate of change of the function as distinct from its average rate of change and is defined as the limit of the average rate of change in the function as the length of the interval on which average is computed tends to 0. After understanding the concept, we will explain the economic uses of derivatives and differentiation.
Let us begin with defining derivative. A derivative is the value of slope of a function at any point. Let there be a function y equal to f of x where the independent variable x changes from x1 to x2 and the corresponding change in the dependent variable y be from y1 to y2 where y1 equal to f of x1 and y2 equal to f of x2. The average rate of change of the function between points A and B is defined as the ratio y1 minus y2 by x1 minus x2 or f of x1 minus f of x2 by x1 minus x2. We can see this ratio is equal to the slope of the chord AB, which passes through the points x1, y1 and x2, y2. As an example, assume that the function y equal to f of x denotes a production function where y denotes the level of output corresponding to the use of x units of labor. The curve of such a production function is shown in the figure. We note that output is 0 when no labor is employed, that is, y equal to 0 when x equal to 0. Further, when x1 units of labor are employed, the level of output is y1 equal to f of x1. Thus, the average rate of change of output when x1 units of labor are employed is given by y1 minus 0 by x1 minus 0 or y1 by x1 or f of x1 by x1. Here, this ratio is represented by slope of the chord OA passing through the points 0, 0 and x1, y1. Very often, we are interested in determining the rate of change of a function when the independent variable x increases slightly from its current value or equivalently. The rate of change of a function at a point in terms of production function considered, such a rate is called the marginal product of labor. To assess the marginal product of labor, we assume that increase in x be denoted delta x and the corresponding change in y be delta y. Thus, the average rate of change can be written as delta y by delta x, or f into x plus delta x minus f of x by delta x. This ratio is termed as the incrementary ratio. Using the concept of limit of a function, we can say that the rate of change of a function at a point is given by the limit of the incrementary ratio as delta x tends to 0. This limit, if it exists, gives the rate of change of the function at point x and is called the derivative of the function y. F of x with respect to x denoted by dy by dx. Thus, dy by dx equal to limit delta y by delta x, where delta x tends to 0, which is further equal to limit f of x plus delta x minus f of x by delta x, where delta x tends to 0. A derivative of a function is also called as the instantaneous or marginal rate of change of the function. Let us now focus on continuity and differentiability. A function y equal to f of x is said to be differentiable at a point x equal to a in its domain if limit of a plus h minus f of a by h, where h tends to 0 exists. Since limit h is equal to 0, therefore limit of f of a plus h minus f of a by h will exist only if limit of f of a plus h minus f of a equal to 0, or limit of f of a plus h equal to f of a. This condition implies that the function y is equal to f of x is continuous at x is equal to a. Hence, we can say that a differentiable function is always continuous. But the converse of this need not be true, since even if limit of f of a plus h minus f of a equals to 0, the limit f of a plus h minus f of a by h may or may not exist. Thus, continuity is only a necessary but not sufficient condition for the differentiability of a function. Next, we discuss the definition of differential and differentiation. Suppose y equal to f of x is differentiable function and delta x denotes an arbitrary increment in x, then f dash x into delta x is termed as differential of y equal to f of x and is denoted by dy equal to f dash x into delta x. The process of obtaining differentials of a function is called differentiation. Let us now understand the concept of derivative briefly and look at some standard derivatives to start with. The basic formulae for most commonly used derivatives are: derivative of a constant is 0. That is, if y is equal to c, where c is a constant, then dy by dx equal to 0. Derivative of a power function. If y equal to x raised to the power n, where n is a real number, then dy by dx is equal to n x raised to the power n minus 1. Derivative of a logarithmic function. 1. If y is equal to log x, then dy by dx is equal to 1 by x. Note, when base of log is not mentioned, it is to be taken as e. Second, if y is equal to log x to the base a, then dy by dx is equal to 1 by x log e to the base a. Derivative of a exponential function. 1. If y is equal to e raised to the power x, then dy by dx is equal to e raised to the power x. Second, if y is equal to a raised to the power x, then dy by dx is equal to a raised to the power x into log a to the base e. Derivative of trigonometric functions. 1. If y is equal to sin x, then dy by dx is equal to cos x. Second, if y is equal to cos x, then dy by dx is equal to minus sin x. Third, if y is equal to tan x, then dy by dx is equal to secant square x. 4. If y is equal to cot x, then dy by dx is equal to cosecant square x. 5. If y is equal to secant x, then dy by dx is equal to secant x into tan x. Sixth, if y is equal to cosecant x, then dy by dx is equal to minus cosecant x into cot x. Let us now understand the rules of derivatives. Rule 1. Derivative of the sum or the difference of the two functions if y equal to u plus minus v, where u and v are both functions of x, then dy by dx equal to du by dx plus minus dv by dx. This rule says that the derivative of the sum or difference of two functions is equal to the sum or difference of the derivatives. This rule can generalize by: if y equal to u plus minus v plus minus w, then dy by dx equal to du by dx plus minus dv by dx plus minus dw by dx. Let us understand the rule with the help of an example. We have to find the derivative of y is equal to x square plus x cube with respect to x. The solution begins as let u equal to x square and v equal to x cube so that u and v are functions of x. Therefore, du by dx equal to 2x and dv by dx equal to 3x square. We can write y is equal to u plus v. Therefore, dy by dx equal to du by dx plus dv by dx equal to 2x plus 3x square.
Rule 2. The derivative of the product of two functions, if y is equal to u into v, where u and v are functions of x, then dy by dx is equal to u into dv by dx plus v into dy by dx. This rule says that the derivative of the product of two functions is equal to the first function times the derivative of the second plus second function times the derivative of the first. As a consequence to this rule, if y is equal to c into u, where c is a constant, we have dy by dx is equal to c into du by dx plus u into dc by dx, which is equal to c into du by dx.
Let us look at an example. We have to find dy by dx for the function y equal to x minus 1 into x plus 3. Then the solution for it is dy by dx equal to x minus 1 plus x plus 3 equal to 2x plus 2. Next we discuss the rule 3, derivative of the quotient of two functions. If y is equal to u by v, where u and v are functions of x and v not equal to 0, then dy by dx equal to v du by dx minus u dv by dx by v square. Consider an example to find dy by dx of the function y equal to 1 plus x square by 1 minus x square. The solution goes as dy by dx equal to 1 minus x square into 2x minus 1 plus x square into minus 2x by 1 minus x square whole square equal to 4x by 1 minus x square whole square. Now let us understand rule 4, chain rule or function of a function rule. If y is a function of u and u is a function of x, then dy by dx equal to dy by du into du by dx.
Taking an example, if y is equals to u square plus 3u minus 2 and u is equals to 2 into x to the power 4, find dy by dx. The solution goes as, by using chain rule we can write dy by dx is equals to dy by du into du by dx. We have dy by du is equals to 2u plus 3 and du by dx is equals to 8x cube. Thus, dy by dx is equals to 2u plus 3 into 8x cube equals to 4x raised to the power 4 plus 3 into 8x cube equals to 32x to the power 7 plus 24x to the power 3.
Next is Rule 5, Inverse Function Rule. If y is equal to f of x and x equal to phi of y are inverse functions which are differentiable, then dy by dx equal to f dash x and dx by dy is equal to phi dash y are reciprocal of each other, that is f dash x equal to 1 by phi dash y or f dash x into phi dash y equal to 1. Consider an example. If y equal to 3x plus 2 by x plus 1, find dy by dx. Solution: dy by dx equal to x plus 1 3 minus 3x plus 2 into x plus 1 whole square equal to 1 by x plus 1 whole square. Using inverse function rule, dx by dy is reciprocal of dy by dx. Thus, dx by dy equal to x plus 1 whole square.
The derivative of an implicit function. Given an implicit function f(xy) is equal to 0, it is not necessary to transform this into an explicit form for the purpose of finding derivative. Such a function can be directly differentiated and the resulting equation is solved to get the desired derivative dy by dx or dx by dy. The method of obtaining derivative from an implicit function is illustrated by the following example.
Example: if ax square plus 2hxy plus by square equal to 0, find dy by dx. Solution: differentiating each term with respect to y, we have 2ax dx by dy plus 2hy dx by dy plus 2hx plus 2by dx by dy equal to 0, or dx by dy equal to minus 2 into hx plus by by 2 into ax plus hy equal to minus hx plus by by ax plus hy. Next we discuss differentials. Use of differentials in approximating errors. The value of a function y equal to f of x when the independent variable takes a value x plus dx is given by f of x plus dx. Here dx denotes a small magnitude of error in measurement of x. Thus, the error in the value of a function when the independent variable is wrongly recorded as x plus dx instead of fx is delta y equal to f of x plus dx minus f of x. This is shown by length of the line AC. Using differentials, it is possible to find an approximate measure of this error. This magnitude, denoted by dy, is given by dy equal to f dash x dx, which is denoted by length dc in the figure. From the figure, we note that the gap between AC and DC will be small values of dx, or in other words, the approximation of error using differentials, we tend to equal to the actual error when dx is small. Use of differentials in linear approximation of a function. Let us assume that y is equal to f of x is a non-linear function, and we want to approximate this by a linear function when x is very close to a value a. From the figure, we can write f of x minus f of a is approximately equal to f dash a into x minus a, where dx is equal to x minus a, or f of x is approximately equal to f of a plus f dash into x minus a. Note that the right hand side of the equation is linear function, that is approximately equal to f of x, a non-linear function. Also note that this linear approximation is also tangent to the curve at the point a, f of a. Let us now discuss use of derivative. Let us look at an example. By using derivatives, show that 1 plus x whole cube equal to 1 plus 3x and 5 by 3x plus 4 whole square equal to 5 by 16 minus 15 by 32 x approximately when x is nearly equal to 0. How good is the approximation when x equal to 0.5? Now let us look at the solution. A linear approximation to the function f of x when x is nearly equal to 0 can be written as f of x approximately equal to f of 0 plus f dash 0 x. For f of x equal to 1 plus x whole cube, we have f of 0 equal to 1 and f dash x equal to 3 into 1 plus x whole square equal to 3 at x equal to 0. Thus, f of x equal to 1 plus x whole cube approximately 1 plus 3x. Similarly, when f of x equal to 5 by 3x plus 4 square, we have f dash x equal to minus 30 into 3x plus 4 whole minus cube equal to minus 15 by 32 at x is equal to 0, f of x is equal to 5 by 16. Therefore, f of x approximately equal to 5 by 16 minus 15 by 32 x. Further, f of x is equal to 5 by 3x plus 4 whole square equal to 5 by 5.5 whole square equal to 0.16 at x equal to 0.5. Its approximation equal to 5 by 16 minus 15 into 0.5 by 32 equal to 5 by 64 equal to 0.078. Error of approximation equal to 0.16 minus 0.078 equal to 0.082. Percentage error of approximation equal to 0.082 by 0.16 into 100 is equal to 51%. Next is the approximation of a function by a polynomial. In situations where the error of linear approximation is large, we may try approximating by a quadratic or higher degree polynomial. First, we understand quadratic approximation. Suppose we want to approximate f of x by a quadratic polynomial when x is close to a value a. We can write f of x approximately equal to alpha naught plus alpha 1 into x minus a plus alpha 2 into x minus a whole square. This approximation is known if the values of the constants alpha naught, alpha 1 and alpha 2 are known. To get the value of alpha naught, we simply put x is equal to a in equation and we get alpha naught is equal to f of a. To get alpha 1, we differentiate equation and put x is equal to a. Thus, f dash x is equal to alpha 1 plus 2 alpha 2 x minus a, or alpha 1 is equal to f dash a. To get alpha 2, we obtained second derivative of equation and put x is equal to a. Thus, f double dash x is equal to 2 alpha 2, or alpha 2 equal to f double dash x by 2. The quadratic approximation can thus be written as f of x is approximately equal to f of a plus f dash a into x minus a plus f double dash a by 2 into x minus a whole square. And when a is equal to 0, the approximation becomes f of a is approximately equal to f of 0 plus f dash 0 plus f double dash 0 by 2 into x square. Next is polynomial approximation. To approximate f of x by a polynomial of degree n when x is close to a value a, we write f of x is approximately equal to alpha naught plus alpha 1 into x minus a plus alpha 2 x minus a whole square,
so on, plus alpha n x minus a raised to the power n.
to find the values of the constants alpha naught, alpha 1, alpha 2, etc. We obtain f of a, f dash a, f double dash a, etc. The values of the constants can be written as alpha naught equal to f of a, alpha 1 is equal to f dash a by 1 factorial, alpha 2 equal to f double dash a by 2 factorial, alpha n equal to.
fna by n factorial.
Thus, we can write f of x is approximately equal to f of a plus f dash a divided by 1 factorial into x minus a plus f double dash a divided by 2 factorial into x minus a
Whole square.
plus f of a raised to the power n divided by n factorial into x minus a to the power n. This expansion is known as nth order Taylor polynomial about x is equal to a. When a is equal to 0, the approximation becomes f of x approximately equal to f of 0 plus f dash 0 divided by 1 factorial x plus f double dash 0 divided by 2 factorial x square plus
fn0 divided by
n factorial into xn. This is known as the Maclaurin approximation. Now we will focus on the concept of differentiation, starting with analyzing its first type, parametric differentiation. If both the variables x and y are functions of another variable t, that is x is equal to f of t and y is equal to g of t, then dy by dx can be.
obtained without the elimination of t.
Using differentials, we can write dy is equal to g dash t into dt, naming it as equation 1, dx is equal to f dash t into dt, naming it as equation 2. Now dividing 1 by 2, we have dy by dx is equal to g dash t into dt by f dash t into dt.
Equals to dy by dt divided by dx by dt.
Next is logarithmic differentiation. If y is equal to f of x is a differentiable function of x, then by using chain rule we can write d log y by dx equal to 1 by y into dy by dx. This can be written as d log y by dx is equal to dy by y by dx, which denotes the rate of proportional change in y. Note that dy by dx denotes the rate of absolute change in y. Further, we learn rate of growth or decay. Let y be a function of time, that is, y equal to phi of t. We can write d log y by dt equal to 1 by y into dy by dt equal to dy by y by dt equal to r Say, here R represents proportional change in Y per unit of time, or the rate of growth or decay of the function. This growth is also known as the compound rate of growth. Now let us apply the concept of differentiation on economic problems. Consumer price index of a certain group of workers increases by 15% per year and their quantity index by 6%. What is the annual growth of their expenditure? Let P denote price index, Q the quantity index, and E the expenditure index. We can write E is equal to P into Q. Taking log on both sides, we get log E is equal to log P plus log Q. Differentiating with respect to t, we get d log E by dt equal to d log P by dt plus d log Q by dt. Let us denote d log E by dt, the rate of growth of E by Re. Similarly, we denote d log P by dt as Rp and d log Q by dt as Rq. Then we can write Re equal to Rp plus Rq equal to 0.15 plus 0.06 equal to 0.21. Hence, the rate of growth of expenditure index is 21%. Next is elasticity of a function. The elasticity of a function y equal to f of x at a point x is defined as the ratio of proportionate change in y to proportionate change in x. Let this ratio be denoted by eta. Then we can write
Eta is equals to dy by y divided by dx by x.
dividing the numerator and denominator by dx, we can write eta is equal to 1 by y into dy by dx divided by 1 by x is equal to d log y by dx divided by d log x by dx equal to d log y by d log x. This implies that elasticity of a function y is equal to f of x can be obtained by differentiating log y with respect to log x. Let us now study about economic applications of derivatives starting with rate of change. Consider a firm producing some commodity in a given period. Let C of x is equal to cost of production x units. R of x is equal to revenue from selling x units. Pi of x is equal to R of x minus C of x is equal to profit from producing and selling x units. We call C dash x as a marginal cost at x and pi dash x as the marginal profit. According to the definition, marginal cost is equal to limit delta x tends to
0 C of x.
plus delta x minus cx divided by delta x. Usually, the firm was produce many units of x. Then delta x is equal to 1 can be considered a number close to 0, and we obtain the approximation of c dash x as c into x plus 1 minus cx divided by 1 is equal to c into x plus 1 minus cx. Marginal cost is then approximately equal to the incremental cost c into x plus 1 minus C of x, that is the additional cost of producing one more unit of x. This is the average rate of change of the cost function C of x. Next is the slope of the tangent. The slope of the tangent to the curve y is equal to f of x at the point a. F of a is given by the derivative of f of x at a is equal to f dash a. We consider an example. Find the slope of the tangent in the figure at point P. Solution. We have f dash a is equal to f of a plus 2 minus f of a by a plus 4 minus a is equal to 2 by 4 equal to half. Thus, slope of the tangent LP at point P is half. Now we understand the demand function. The demand of a commodity in a given time period depends upon its own price, price of other commodities, income of the consumer, etc. We define three types of relationships as follows: 1. Price demand, 2. Income demand, 3. Cross demand.
Let us now start with the price demand function. The relationship of demand of a commodity with its own price is termed as the price demand or the law of demand. Other things like income of the consumer, price of other commodities, tastes and habits of the consumers, etc. remaining constant, the quantity demanded of a commodity, that is xt, varies inversely with its price. Mathematically, we say that xt is a function of p. Since xt decreases as price increases, we have xt by dp less than 0 under normal conditions of demand. The price elasticity of demand, or simply the elasticity of demand, is defined as the negative of the ratio of proportionate change in the quantity demanded to the proportionate change in the price. It is denoted by eta, where eta d is equal to minus d log x by d log p. We can also write eta d equal to minus d log x by dp into dp by d log p, which is equal to minus 1 divided by x into dx by dp into p, which is equal to minus dx by dp into p by x. Second, the income demand function or angel function. The relationship of demand of a commodity with the income of a consumer is termed as income demand function. Assuming the price of the commodity and prices of other commodities, etc. as constant, we say that quantity demanded x of a commodity is a function of the consumer's income. Symbolically, we write x is equal to gy. Note that dx by dy can be positive or negative depending upon the nature of the commodity. If dx by dy is greater than 0, the commodity is said to be a normal good. If dx by dy is less than 0, the commodity is said to be an inferior good. The income elasticity of demand. The income elasticity of demand, eta y, is defined as the ratio of proportionate change in quantity demanded to the proportionate change in income. Eta y is equal to d log x by d log y, which is equal to d log x by dy into dy by d log y, which is equal to dx into dy into y by x. Note that for eta y being positive, the commodity is normal and for eta y being negative, the commodity is inferior.
Income elasticity of demand. The income elasticity of demand given as eta y is defined as the ratio of proportionate change in quantity demanded to proportionate change in income. That is, eta y is equal to d log x by d log y equal to d log x by dy by dy by d log y equal to dx by sy into y by x. Note that when eta y is greater than 0, then the commodity is normal, and when eta y is less than 0, then the commodity is inferior.
The cross demand function, the relationship of the demand of a commodity with the price of other commodities, is termed as cross demand function. Let there be two commodities A and B, assuming other things as constant, and we can write demand for A denoted by XA as a function of the price of B, which is PB, and also the demand for B, XB, as a function of the price of A, that is PA. Such functions are termed as cross demand functions. We note that if dXA by dPB is positive and dXB by dPA is positive, then A and B are terms as substitutes. If dXA by dPB is negative and also if dXB by dPA is also negative, then A and B are terms as complements.
Cross elasticity of demand. The cross elasticity of demand of commodity A as compared with price of B, denoted by eta AB, which is a ratio of proportionate change in quantity demanded of A to a proportionate change in price of B. Symbolically, we can write eta AB equal to d log XA by d log PB equals to dXA by dPB into PB by XA, and eta BA equal to d log XB by d log PA is further equal to dXB by dPA into PA by XB. Next is the law of supply. Other things like prices of other commodities, prices of factors of production, level of technology, etc., kept constant. The quantity supplied XS of a commodity varies directly with its price. Mathematically, we say that
XS
is a function of P. Note that dxs by dp is greater than 0. Now we understand the elasticity of supply. The elasticity of supply is defined as the ratio of proportionate change in the quantity supplied to the proportionate change in price. Eta s equal to d log x by d log p is equal to dx by dp into p by x. Let's take an example. Find the elasticity of supply for the function x is equal to 2p plus p square at p is equal to 5. Solution: the supply function is x is equal to 2p plus p square, then dx by dp is equal to 2 plus 2p. At p is equal to 5, dx by dp is equal to 2 plus 2 into 5 is equal to 12, and x is equal to 10 plus 25 is equal to 35. Thus, elasticity of supply equal to dx by dp into p by x equal to 12 into 5 by 35 equal to 1.71.
Let's look at another example. Show that for the inverse supply function P is equals to A plus Bx, where B is greater than 0, the supply is elastic if A is greater than 0, inelastic if A is less than 0, and unitary elastic if A is equal to 0. Solution: given P is equals to A plus Bx, we get dP by dx is equals to B. Eta s is equals to dx by dp into p by x is equals to 1 by b into a plus bx divided by x is equals to a by bx plus 1. Since b is greater than 0 and x is greater than 0, elasticity of supply will be greater than 1 if a by bx plus 1 is greater than 1 or a by bx is greater than 0. This implies a is greater than 0. Similarly, elasticity of supply will be less than 1 if a by bx plus 1 is less than 1 or a by bx is less than 0. This implies a is less than 0. Elasticity of supply is equal to 1 if a by bx plus 1 is equals to 1 or a by bx is equals to 0. This implies a is equals to 0.
Let us now understand the concept of revenue function. Let P is equal to f of x be an inverse demand function. The total revenue, denoted by TR, is defined as a function of x. Using symbols, we can write TR is equal to P into x is equal to x into f of x. On differentiating TR with respect to x, we get instantaneous rate of change of total revenue, termed as marginal revenue, MR. So, MR equal to d into TR by dx is equal to f of x plus x into f dash x, and average revenue AR is defined as AR equal to TR by x equal to x into f of x by x equal to f of x. Next is the short run production function. We assume that in the short run, labor is the only variable factor of production. Thus, we can write the total product of labor, denoted by x, as a function of the units of labor L used. That is, x is equal to TPL is equal to f of L. This function is termed as the production function. The average product of labor APL is equal to f of L by L equal to x by L. The marginal product of labor MPL is equal to D into TPL by DL equal to dx by DL equal to f dash L. In short run, we have the law of variable proportion, which states that as the amount of a variable factor, labor, is increased, keeping the amount of other factors as constant, the output X first increases at an increasing rate, that is dx by dl greater than 0, and d square x by dl square is greater than 0, then after a certain point it increases at decreasing rate, that is dx by dl greater than 0 and d square x by dl square is less than 0, and finally starts declining, that is dx by dl less than 0. Next is the elasticity of output. Given the production function x is equal to f of L, the elasticity of output is given by ratio of proportionate change in output x to proportionate change in the use of input or labor n in this case. Thus the elasticity of output denoted by epsilon is given by d log x by d log L equal to dx by dl into L by x equal to dx by dl divided by x by L equal to MPL by APL. Further, we discuss the elasticity of average product. We can write the average product of labor as APL is equal to x by L. Taking log on both sides, we have log APL is equal to log x minus log L. Differentiating both sides with respect to log L, then we have elasticity of APL is equal to d log APL by d log L is equal to d log x by d log L minus 1 is equal to epsilon minus 1, which can also be written as equal to MPL minus APL by APL. Now we understand the marginal revenue product. Let P is equal to f of x be an inverse demand function and x is equal to f of L be a short run production function. Then TR is equal to x into f of x is an indirect function of labor L. The derivative of TR with respect to L is known as marginal revenue product of labor, denoted by MRPL. Using chain rule, we can write MRPL is equal to D into TR by DL equal to D into TR by DX multiplied by DX by DL equal to MR into MRPL, which is further equal to AR into 1 minus 1 by eta into MPL, where MR is equal to AR into 1 minus 1 by eta.
Let us now summarize what we have learnt in this module. A derivative is the value of slope of a function at any point. It is also called as the instantaneous or marginal rate of change of the function. A differentiable function is always continuous. Suppose y is equal to fx is a differentiable function and delta x denotes an arbitrary increment in x, then f dash x into dx is termed as the differential of y and is denoted by dy is equal to f dash x into dx. The process of obtaining differentials of a function is called differentiation. It is used for approximating errors. Differentiation is extensively applied in economics.